Hi, I'm Bill Webb, and we'd like to talk now about blending special relativity into optics. This turns out to be a very big and exciting field. Uh, the problem currently is that physics is teaching that photons traversing through a material actually interact with the materials at point like electrons and cause a slow velocity with a refractive effect. But anytime that you interact with a point like electron, you expend energy, and the photon consequently loses energy. And we know from current fiber optics that photons can travel for miles through fiber optics without losing energy. So something's wrong with this interacting concept. It doesn't meet the tests of modern optics. You can go online and use Wikipedia and look up index of refraction, and you'll get an explanation of this this shaking process, interacting shaking process, still being used today by people performing index refraction studies. That problem is resolved by photon-circle electrons, and the photon-circle electrons in a transparent material are relativistically warped. All of those photon-circle electrons are relativistically warped, and each warped photon circle has a field of warpage, and that field of warpage warps, that is to say, it slows and bends approaching and traversing photons. So when a traversing photon enters a material, it's warped by the field of warpage at the surface of the material. Then it's warped while it's in the material, and when it exits the material, it dewarps. So photons approaching, traversing, and exiting, they're first warped and then dewarped, and they complete this travel without any loss of energy. We've shown that photon-circle electrons in a material are warped and produce a surrounding field of warpage. And here's a for instance. If you take a helium atom and remove one of its two electrons, you're left with a helium ion that has only one electron, and that helium ion becomes warped to a spatial angle of warpage of 60 degrees. This photon-circle electron is actually warped to half of its rest size. Its mass is increased by a factor of 2, warped to by a factor of 2, and its time has been slowed by, dilated by a factor of 2. It's a very highly warped electron in a helium ion. A hydrogen atom's photon-circle electron is warped to a very small amount, less than half of 1 degree. In the full helium atom, the twin photon-circle electrons have been calculated, both of them being warped to 30 degrees. So a reasonable large amount of warpage. It's interesting to use the equation of warpage for the index of refraction. And that equation can be used to determine the average warpage of a material. For instance, a very dense diamond material, a diamond is like a lady wears on her finger, has an index of refraction of a very high index of refraction of 2.418, and using the equation for the index of the warpage of the index of refraction, we can calculate that the angle of warpage is very large at nearly 50 degrees. The field of warpage from the surface electrons of a material extend outside of the material. And so if you have a photon approaching a glass block, for instance, before that photon gets to the glass block, it encounters the field of warpage from the surface electrons and actually does its bending and slowing before it gets to the block of glass. So the warpage is actually an external affair. Once the photon gets inside of the glass, it continues to be warped because it's in a more or less uniform field of warpage. And then, of course, when it exits the glass, it dewarps. In this case, the glass has a index of refraction of 1.457 and a calculated average field of warpage with an angle of 34.06 degrees. The important thing to remember is that the warpage takes place actually outside of the glass before it enters the glass. The subject of total internal reflection then gets changed a little bit. Here we have a photon that is traveling inside of the piece of glass, and it arrives at an angle that is larger than the critical angle. And rather than simply totally internally reflecting at that point, that photon actually escapes out of the surface and is acted on by the field of warpage on the outside of the glass and is caused to deflect and turn back into the glass. So as a matter of fact, total internal reflection might more correctly be called total external refraction. We can do an experiment to illustrate that there is actually an external field of warpage. I have here a experimental model, desktop model, and it's got a laser mounted here, and when we rotate this, we can see the field of warpage being illustrated by all of these photons that escape and come up above the surface of the glass. In order for this to be achieved, it's necessary that the glass has an external field of warpage as was shown up here. And that field of warpage has a wide range of indices of refraction. The next subject that illustrates the same phenomena is an illustration of diffraction. We show 24 coherent red photons acting, impinging on a diffraction grating. The openings in the diffraction grating are about the same size as the wavelengths of the photons, and the distance between the two openings is about twice the length of photon's wavelength. 18 of these photons, 6 there, 6 there, and 6 there, are absorbed into the material of the diffraction grating, and 6 pass through the diffraction grating, and it's quite obvious now what happens. The ones that are closest to the material are momentarily slowed and warped to go through a curved path in 4 different locations. The ones that are in the middle of the slit are momentarily slowed but continue on in a straight direction. And if those 6 photons were allowed to fall on a screen above what's shown here, they'd form a diffraction pattern. Very nice. Reflection turns out to be something that you might have to think about a little bit. But what happens in reflection, if I have a smooth, opaque, reflective material here, like a piece of silver, polished silver. It would have a field of warpage outside of the surface of the silver, and an incident photon would come down and go through a partial photon circle and redirect, going away at the same angle as the incident angle. The key thing being here that there's a partial photon circle executed by the photon to make it reflect. If we use a short enough wavelength X-ray photon with enough energy going into the field of warpage of a opaque material, that is to say, it has an index of refraction very high index of refraction. It's actually opaque. It won't transmit the photons. This X-ray photon then impinges into the field and is caused to form a photon circle and change and transmute from a photon to a photon-circle electron. The transmutation requires the energy of the photon to be equivalent to the photon circle's mass energy, and if you go through the calculations, you determine that the wavelength of the X-ray has to be of that value. The ratio of that value's wavelength to the electron's resting circumferential length just turns out to be the number alpha, the fine structure constant. A very neat calculation. Photons and photon circles synthesize. Photonics has done a beautiful job of discovering lasers, and lasers are just simply a collection of photons that have been synthesized to occupy the same space at the same time. Well, photon circles are a variety of photons, and they also synthesize. Here's what I've found out so far. Numerous photon circle electrons synthesize with photon circle positrons to build the three photon circle quarks that make up a neutron. The neutron then decays and produces a photon. The neutron's decay is the emission of a photon circle electron. Going even further, numerous neutrons synthesize to build a more massive neutronium A, which then decays by emitting both photon circle electrons and photon circle positrons, and it becomes the nucleus of a far more massive atom with mass number A. And a little bit further on, muons, things like muons, mesons, baryons, gluons, etc. All of these are believed to be collision-produced synthesis of photon circles. In summary of what we've learned on the previous 7 pages, photon circle electrons in materials are relativistically warped. Then they have extended fields of warpage, and that warpage will warp approaching, traversing, and exiting photons. The field of warpage from photons, electrons, the field of warpage of the photon circle electrons extends outside of the material surface, so that an approaching photon is acted on outside of the material by the accumulated 1 over r squared field of warpage of the material's surface molecules. And then refraction, internal reflection, diffraction, reflection, photon circle production, all of these are used to illustrate the warping of photons by the fields of warpage. Photon circles synthesize in a fashion similar to the synthesis of photons by the laser process. Photon-Circle Electrons have blended special relativity into optics, and if you want to do correct optics, you have to include the warpage of special relativity. Thank you.